Hello, everyone. How are we doing? Hope everything's going good. We're starting Unit 3 today, which is super exciting. So 3.1 is what we're looking at, which is all about exponential functions. I always got made fun of last year because I say exponential. Like I say it weird, I guess. Anyway, so this whole unit is all about exponential functions and log functions, so that'll be super fun. But specifically today, we're just going to review some exponential functions. So we have 4 objectives for today. The first one is to recognize and evaluate exponential functions with a base of a, so a number, right? Then we're going to look at how do we graph those exponential functions with a base of a. So those 2 are review. Then we're going to be able to recognize, evaluate, and graph exponential functions with a base of e. And then the last one is we're going to use exponential functions to model and solve real-life problems. Okay, so we're going to look at some word problems here. Okay, so the first thing is that we have to review what is an exponential function. Okay, so here f of x equals a to the x, or y equals a to the x is our exponential function. I believe in algebra 2, we used y is equal to a times b to the x. I want to say that that's what we used, where a in this case is b over here, but a, whatever is being raised to the power of x, has to be a positive constant other than 1. Okay, and x is a real number. So just a quick little review. If we go down, using our calculators, we're just going to approximate each of these numbers. So we can just plug these into our calculators, right? When x is negative 3.1, so I have f of negative 3.1. I'm just going to enter 2 to the negative 3.1 into our calculator. And that's it. Nothing too crazy, right? And I get approximately 0.117. So check your work there. We're rounding to 3 decimal places, right? So check your work to make sure that you're entering those correctly. Go ahead and try the other 2 for pi. You do have a pi button on your calculator, so make sure you use that pi button and not just 3.14, because that's not pi, right? And then for 3 over 2, make sure you put that in parentheses. But other than that, plug these in, check your work. Good luck. All right, so hopefully we got these answers here. Another option that you could have done for this third one, you could have done 0.6 to be 1.5 if you didn't want to enter a fraction, right? 3 over 2 is 1.5, so that's another option too. But hopefully we feel good just about entering these numbers into our calculator. So let's look at graphing. It says graph each function by creating a table of values. Okay, so I'm going to do the first one in pink. XY wants me to create a table of values. So if I plug in negative 2, and I'm going to do the work over here, I have 2 to the negative 2. And if we go back and we remember all of our rules of exponents from algebra 2, this is the same as 1 over 2 to the positive 2, right? I can bring this to the bottom of the fraction and make it positive. So I get 1 over 4. So if I plug in negative 2, I get 1/4. If I plug in negative 1, right? 2 to the negative 1 is the same thing as 1 over 2 to the positive 1, which is just 1/2. So negative 1 is 1/2. 0 to anything to the 0 is 1, except for 0. If I plug in 1, 2 to the 1 is 2. If I plug in 2, 2 squared is 4. If I plug in 3, 2 to the 3rd is 8. And I can keep going, but I probably can't fit any more on here. So negative 2, 1/4. negative 1, 1/2, 0, 2. Well, sorry. 0, 1, 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. So there is my graph. And I'm going to make sure to label this. Y is equal to 2 to the x. So there's my graph. Okay, now I'm going to do 4. So I'll switch up the color here. So x and y. So negative 2, right? I have 4 to the negative 2, which is the same thing as 1 over 4 to the positive 2, which is 1/16. So if I plug in negative 2, I get 1/16. If I plug in negative 1, I get 1 over 4 to the 1, which is just 1 over 4. 0, I get 1. If I plug in 1, 4 to the 1 is just 4. If I plug in 2, 4 squared is 16. 3, 64. I know that those points aren't going to fit, but it's fine. Okay, so now I have negative 2, 1/16, which is like real tiny, right? Negative 1, 1/4, 0, 1, 1, 1, 2, 3, 4. And then my next point is like way up here at 16. So when I when I graph this, I need to make sure that it doesn't cross over this 2, because it doesn't hit 2 until like way up here at 16. So this is the equation y is equal to 4 to the x. Okay, so what we're really looking at here is notice that if my a value, or my base, right, this is called my base, if my base is bigger, the graph is more steep. As my base gets smaller, the graph gets more flat. Okay, so that's something just to keep in mind here. Okay, so we're going to clear this. I want you guys to try this, but now you're going to try it with these two, which is negative x. So it's 2 to the negative x and 4 to the negative x. Okay, actually, let's just do it together. Let's just do it together. I'm going to do the 4 first, since I already have the blue color up. Now, again, I'm going to go negative 2, 0, 1, 2. I don't really need more than that. Okay, so if I plug in negative 2, I have 2 to the negative 2, right? Because this negative is right. Oh, I'm looking at the wrong one, sorry. But the negative is right there, right? So this is really 2 to the positive 2, which is 4. Then I have 2 to the negative 1, which is really 2 to the 1, which is 2. And then 0, well, it's still 1. If I plug in 1, I have 2 to the negative positive 1, which is 2 to the negative 1, which is 1/2. Oh no, I'm doing 2s. Sorry, guys. This is just how I live my life. It's fine. Okay, so this is 4, this is 2, this is 1, this is 1/2, this is 1/4. I am so sorry. I'm the worst. It's fine. It's fine. Okay, so then for the blue, it's going to be 16. There we go. 4, 1, 1/4, 1/16. So let's graph the blue one first, since I'm there. Negative 2 doesn't fit. Negative 1, 1, 2, 3, 4, 0, 1, 1/4, 1/16, real tiny, right? And then I'm going to make sure I don't cross over 2. So there's the graph of y is equal to 4 to the negative x. And if I go back to my pink, I have negative 2, 1, 2, 3, 4, 5, 6, 7, 8, negative 3, 8, negative 1, 2, 0, 1, 1/2, 1/4. Great. And then that's the graph of y equals 2 to the negative x. Okay, so it's asking me here, what do we notice about 2 to the x and 2 to the negative x? And hopefully we notice that they are reflections of each other. They are reflected over the y-axis, right? Positive 2 was doing this, just to show you, right? That was y is equal to 2 to the x. Okay, so they are reflections of each other. So hopefully that's what we noticed. Okay, so we can say they are reflections of each other, and we can be more specific with that because we know that they're reflecting over the y-axis, right? They are reflecting over the y-axis. They are flipping over the y-axis. Then it's asking what's the domain, range, y-intercept, and horizontal asymptote. So I'm going to clear this and go down, and we're just going to have to look at the image on the previous page, right? The domain of this. How far to the left do I go? Well, I go all the way to negative infinity, right? How far to the right do I go? So keep in mind the graph looks something like this. Okay, how far to the right I go? Well, it's also infinity. So my domain is that x is in the set of all real numbers. Okay, then we look at range. Okay, here, what's the lowest I go? Well, this graph never crosses over the x-axis. So the lowest I can ever get is 0. Now, can I ever get to 0? No, right? If I keep dividing by 2, dividing by 2, dividing by 2, dividing by 2, will I ever get to 0? No. Okay, so my range is 0, and then the highest I go is infinity. And notice that I have a parenthesis at 0 because I cannot ever get to 0. Can't get to 0. Okay. Then the next question is, what is the y-intercept? Where does this graph cross the y-axis? And it should recognize that it crosses at 0, 1. And then the other question is, where's the horizontal asymptote? Well, we just said the graph never gets to 0, right? So that means that there's a horizontal asymptote at 0, y equals 0, which is just the x-axis. Okay. Hopefully it's a nice little review. Let's keep going and look at example 4. Example 4 says to graph each function by transforming the graph of y equals 3 to the x. Okay, so let's start with figuring out what each of these things do. And let's make a little note of it. Do we have it somewhere else too? Okay. So if I have a plus or minus up in the exponent, that is my horizontal shift. So this is my horizontal. I don't know why I put an H there. It's nap time. Okay, horizontal shift. Okay. And hopefully we remember that with horizontal shifts, you always go the opposite direction, right? If I were to set x plus 1, you don't have to write this part, but if I were to set x plus 1 equal to 0 and solve, I would get x is negative 1. So this tells me that I'm going to move left 1 unit. So let's go through and write down the parent points, and I'm going to do that in yellow. The parent points of this graph, okay? So it's 3 to the x, so negative 2 would be 1/9. Negative 1 would be 1/3. 0, 1, 1, 3, and 2, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that doesn't fit. So here's my parent points. So then if I want to transform these or translate them, I'm just every single point is going to go to the left 1 unit. And there's my graph. That's it. Not so bad. Okay. If I have a plus or minus outside of the exponent, right, this is just on the end, this is my vertical shift. And if we remember vertical shifts, they always just go in the direction that you see. So since that's a -2, this is going to go down 2 units. So again, I'm going to draw the parent point. So 1/9, 1/3, 0, 1, 1, 3. So those are my parent points. And then these are just going to come down 2 units. There we go. And then you have to ask yourself what also comes down 2 units. And hopefully our first thought or a thought is the horizontal asymptote also comes down 2 units. So I have to redraw that back in. So there's my horizontal asymptote. And then I can draw the graph. Oh, and I can say 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that 9th term fits. So that's exciting. Did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So hopefully we feel good there. When I have a negative out front, just like with parabolas, this is an x-axis reflection. X-axis reflection. So again, if I plot the parent points, 1/9, 1/3, 0, 1, 1, 3. Okay. All I'm going to do here is reflect everything over the x-axis. So negative 1/9, negative 1/3, negative 1, and negative 3. So now the graph is just opening down instead of up. So all these rules are the same as parabolas. Okay. And then the last one is if the negative is up top in the exponent, that's my y-axis reflection. Okay, so again, last, I'm going to plot the parent points. You don't have to plot the parent points. If it helps you, yeah, woohoo, go for it. If it doesn't help you, then don't do it. I don't care. Okay, but now I'm going to go over the y-axis. So now it's going to be over here at +2. And then +1, 1/3. The 0, 1 stays. And then -1, 3. And so now the graph is opening to the left. Sorry, to the right. How do we feel? Nice little review of exponential functions. Yeah? Woohoo? Okay, if you need help on base of a, right, in this case it was 3, but a base of a number, please reach out and make sure that you let me know so that we can work on it. And then, yeah, because I don't want you to get behind just because you're not feeling confident in exponential functions. And let's move on. Okay, so now we're going to look at E, which is called the natural base. And right here, this is called the natural base. And E is similar to pi, right? Pi is a symbol that represents a number, 3.14159, blah, 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 right? So pi represents a number. E also represents a number, and here it is right here. 2.7182818281828, and so on and so forever. Okay, so when we're talking about a natural exponent, we're using, it has a base of e instead of a base of a number. So instead of 3 to the x or 4 to the x, it's e to the x. Okay, so we're just going to practice, and you do have this button on your calculator. So I'm going to bring up my calculator here and show you where it is, and then we can look at evaluating these. Okay, so on our calculator, the E button is located right here under pi. So it's second divide to get to the E button, okay? So if I want to evaluate e to the x at x squared, it's just, I'm just looking at f of 2 is equal to just e squared. So then I can just pull up my calculator and say that e squared. Just hit enter, and there it is, 7.389. In this case, they want me to round probably the 3 decimal places like we did last time, so 7.38. So go ahead and do the other two, and then check your work. Okay, so check your work here. Hopefully we feel good about entering this into our calculator and evaluating. Next thing that we're going to look at here is graphing. So how do we enter this into my graphing calculator? So let's go ahead and clear these and look at the next example, which is all about graphing. So it wants us to sketch the graph of each of these natural log functions. Sorry, not natural log, natural exponential functions. So like for real, I would just enter this into my graphing calculator and then use the table feature on my graphing calculator. So let me show you what I mean. If I go to y equals, clear out anything that you might have, and I'm going to enter this function, 2, and then times e to the 0.24x. Just like that. And I don't really need to know what the graph looks like. I only want the table, right? Because I have to fill out this table of values. So I'm going to go second graph, because then that gets me this table feature. And then here's all my values. It wants me to start at -3, so there's -3. And then all the way up to 3. So I can just enter these numbers into the table and then plot the points and graph it. So go ahead and try A and B here, right? Find the values from the table, enter them here onto this table, and then just graph those points and connect it. When you are ready, go ahead and hit play. Alrighty, so let's check our work here. Check your table values. Make sure that you entered your equation correctly. Make sure that you read your table correctly. And then I just plotted the points, and this one didn't turn out very well, but you get the idea of what those look like. So because this 0.24x is positive, the graph is increasing from left to right. And because this negative 0.58x is negative, the graph is decreasing from left to right. So that's kind of it on that. The last thing we're going to look at is some application problems, like how do we use this in the real world. And then we do have one page of mixed review where I just want to review a couple of the old concepts with you to make sure that we're feeling really good about them. So let's clear this out. So in the real world, we use this a lot when we're talking about interest. So we're going to look at these interest equations. I know that we talked about this in Algebra 2, but we're going to go over it again, because why not? We can, right? So two different formulas for interest here, but I want to just go over after t number of years. So the t in the equation is years. A balance A in an account with a principal. Principal is your P. It's what you're starting with. Okay, so the P is how much money in your account that you start with. and then your annual interest rate, R, and that has to be in decimal form. So I'm going to underline that. That's so important. R has to be decimal. So if I'm talking about like 8%, right? What is 8% as a decimal? It's 0.08, right? Or if I'm talking about like 12%, what is that as a decimal? It's 0.12, right? So just making sure that we feel really confident in going from percent to decimal. So if I am getting interest compounded every year, once a year, or twice a year, or 3 times a year, or so, whatever, right? I'm going to use this top formula. And this top formula, the N is how many times a year you compound the interest. And it will tell you that in the problem, okay? If I'm compounding continuously, so I'm literally 24/7, 365, like compounding interest continuously, I'm going to use this equation that has the base of E. Okay, so when we look at problems, it'll tell you how the interest is being compounded, so then you'll know what equation to use. Okay, so let's look at this first example, example 8. Which says a total of $9,000 is invested at an annual rate of 2.5% compounded annually. So this tells us that it's compounded one time every year. Find the balance in the account after 5 years. So since it's being compounded annually, we're going to use that first equation. So P times 1 plus R over N, and then N to the T. Sorry, time to the N times T. And I'm just going to plug in my values. So my principal is what I start with. That is $9,000. And I have 1 plus 2.5% as a decimal. So 2.5% as a decimal. I move the decimal place over twice. And I get 0.025. So this is 0.025 over N is the number of times a year it's compounded. Well, it tells me right here it's compounded annually. That means once a year. And then N again is 1 times T, which is in this case 5. I want to know how many or how much money is in there after 5 years. So now it just becomes a calculator game, right? I do 0.25 divided by 1, which is just 0.025. And then add 1, right? So this is 9,000 times 1.025 to the 5th. And I'm going to do this part first. Exponents before multiplication, right? I'm using our order of operations. So I do 1.025 to the 5th in my calculator. And then I multiply that number by 9,000. And I get about $182.67. And that is how much my account will, or my investment will be worth after 5 years. Okay, so hopefully that makes sense, right? This should look decently familiar doing these types of problems. I want you, oops, sorry, too far. I want you guys to try example 9. Example 9, you're gonna be doing this twice, right? We have $12,000 invested at an annual rate of 3%. Find the balance in the account after 4 years. One, if the interest is compounded quarterly, so N will be 4. And then B, part B, where it's compounded continuously, and you would use that equation with E as the base. So just try it. If you mess up, no big deal, but give it a shot, and then when you're ready, hit play and check your work. Okay, let's check our work here. For the first one, we're using this first equation, keeping in mind that my rate, my interest rate, right, my annual rate has to be in decimal, so that should be 0.03. And then N is 4 because I'm compounding quarterly, so that's 4 times a year. And then I want after 4 years, so I multiplied by 4. And we should have gotten about $13,523.91. Then for B, I'm using the second equation because it's compounded continuously, so nonstop, it just keeps compounding. And then so here, my P was 12,000, here's my E, and then my R is still 0.03, and my T is 4. And so I do that, and I get about $13,529.96. So only about a $6 difference between the two. If you have questions on those examples, let me know. Hopefully, like I said, they look familiar, and we're feeling pretty confident there. Let's do our last couple examples, and then we'll look at the mixed review. Example 10 says, let Y represent a mass in grams of a radioactive strontium whose half-life is 29 years. So what that means is every 29 years, the amount that you have cuts in half. Sorry, my dog is under me. Is it the computer's? Okay, there we go. Okay, so every 20, if I start with 100 grams or whatever, right? After 29 years, I'll have 50. And after another 29 years, I'll have 25. And after 29 years, I'll have 12.5, right? So the quantity of this is given by the equation. So we already know the equation, which is really nice. Here it's asking, what is the initial mass? How much did I start with? And looking at the equation, we shouldn't even have to plug in T is 0, right? Because looking right here, this is always my initial value. So we should just be able to say that it's 10 grams. If you are unsure and you plug in 0, just to do it real quick to show you, if I plug in 0, well, 0 over 29 is 0. So this just is 1/2 to the 0. Well, anything to the 0 is 1. So this is just 10 times 1, which is 10. So if you plug in 0, you get the same answer, but hopefully we are aware enough of our equations to know that my P value, right, my A term here, is my starting value. And then part B says, how much of the initial mass is present after 80 years? So now I'm going to plug in 80, right? So I want Y of 80. So I have 10 times 1/2 to the 80 over 29, which I can just enter into my calculator, and I'm going to get an approximate 1.478 grams. So check your calculator skills on that. Try to enter it and make sure that you get 1.78, 1.478 grams. Okay, we're going to do the same thing for example 11, more or less. Okay, the same thing. The approximate number of fruit flies in an experimental population after T hours is given by the equation Q of T. Find the initial number of fruit flies in the population. Well, again, I could plug in 0, or hopefully we have enough common sense to look at our equation and be able to tell that there are 20 fruit flies in the initial population. Okay. Then it says, how large is the population of fruit flies after 72 hours? So now I want to find Q of 72, right? Because T is hours. So I have 20 E to the 0.03 times 72. And I enter that into my calculator, fun stuff, and I get 173.422-ish. You can't have 0.422 fruit flies, so I would say approximately 173 fruit flies. Even if it was, just to write underneath, even if it was like 173.9, it would still be 173 because 0.9 fruit flies is still not a whole fruit fly, right? So I have 173 whole fruit flies. So hopefully that makes sense why we always round down there. And then the last thing, it says graph Q. Well, I could plug this into my graphing calculator, which is be easy. Okay, So this is T in hours. And then up here is Q, which is number of fruit flies, but I can't fit that. So, okay. So I'm gonna go 1, 2, 3, 4. Okay, so I know that if I call this 72, then I can call this 200, right? Then this is 100. I know that there's 173 at 200, so ish. And then I know at 0 that there's 20, so this is 50, so then here's 20-ish. And 2 points is enough to sketch it, but if you want more points on your own, then you can use the table feature on your graphing calculator, or you can just plug in other points. Okay, so that's it for 3.1. However, we are going to go over the mixed review slowly. Actually, probably not slowly, probably pretty quickly, since it's all mixed review. But we are going to do one more page here, which is all on the mixed review. So 5 problems here. First problem says determine whether the quadratic function has a minimum or maximum. Then find the coordinates of the minimum or maximum. So the first thing that I want to look at is, does this open up or down? And this parabola in this case opens down, right? I guess down. So since it opens down, so let's write this, right? Opens down. So since it opens down, it has a maximum. So it has a maximum. So there's the first part. I found that it's a maximum, right? Because if it's opening down, then the maximum is up top. Then it wants me to find the vertex, essentially, find the minimum and maximum point. So to find the x-coordinate of the vertex, I can use my negative b over 2a formula, which I believe we did in unit 1, I want to say. Okay, so in this case, negative b is going to be positive 6, and then 2 times negative 3, because negative 3 is a. So I have 6 over negative 6, which is negative 1. So the x-coordinate of the vertex is at negative 1. Now in order to find the y-coordinate, I'm going to plug in negative 1, f of negative 1. So I have negative 3 times negative 1 squared minus 6 times negative 1 plus 8. Negative 1 squared is 1, so this just stays negative 3. Negative 6 times negative 1 is positive 6 plus 8, and we should get 11. So the vertex, or the maximum, is at the point negative 1, 11. Hopefully we feel good. Yeah, right? Next one is from Unit 2A. Find the roots and graph the function. Well, since this is a degree of 3, I'm going to have to graph it first. Okay, so let's bring up our graphing calculator and graph it. So 2x cubed plus 3x squared. Oh gosh, how did that happen? There we go. Plus 3x squared minus 8x minus 12. Now I'm going to graph it. Okay, so I can clearly see that it crosses the graph, or it crosses the x-axis at negative 2. These I'm not really so sure about, but this one's pretty clear that it's negative 2. Or, sorry, positive 2. So I'm going to use synthetic division, and I'm going to divide by 2. Okay, so 2. This gives me 2, 3, -8, -12. And quick synthetic division, bring down the 2. I'm going to multiply and add, and multiply and add, and multiply and add. And I should get 0, right, on the bottom. So now I'm left with 2x squared plus 7x plus 6. And this is something I can either use quadratic formula or I can factor. I know that this one is factorable, so I'm going to go ahead and factor. I'm going to multiply the first and last terms together, so I get 12x squared. 7x is in the middle, and I'm looking for two numbers that multiply to 12 and add to 7. And so that's going to be 3x and 4x. And I'm going to go into my box. So, sorry, I'm down. So I have 2x squared on the top left, 6 on the bottom right. Fill in with the 3x and the 4x. Greatest common factor of this top row is x. So that leaves me a 2x on top and a 3 on top. And then a 2 down here, and 2 times 3 is 6, so I'm good. Okay, so if I write this in completely factored form, don't forget my f of x, I have x minus 2. I know that that is 1 because of this positive 2, right? It's always x minus. And then my other two parentheses, here I have an x plus 2. And the last one is 2x plus 3. So this tells me that I have x-intercepts at 2, at -2, and at -3/2. And all of these have a multiplicity of 1, which also tells me that they are going to just cut straight through, no bouncing. And then the last thing is I need to know the end behavior. Well, the highest degree is a 3, and this 2 is positive, so that tells me that my ends are doing this. Okay, so I have, this -2. So then here's +2. So I have a point here at -2. I have a point at -1.5, and I have a point at 2. So the graph comes down, cuts through, turns, cuts through, turns, cuts through. Something like that. The ends are doing what I wanted them to do, right? And I'm cutting through every single time. Hopefully we feel good there. Nice little review. Excuse me. Okay. All right, moving on to question C. Find the nth degree polynomial. In this case, n is 3. So we're finding the third degree polynomial function with real coefficients and no imaginary numbers, with the zeros 2 and 3i. So we have to remember if 3i is a 0, then -3i is also a 0. Right? The complex conjugate is also a 0. And then very specifically, we have this extra parameter that if I plug in 1 to this function, whatever the function is that we find, I have to get out -9. So when we go to write this, we can start with the factors that I'm given. I know that I have x minus -2, right? I know that I have x minus 3i, and I know that I have x minus -3i. And then if I wasn't given this information, I could just multiply this out and call it a day. But since I'm given this specific information, I need to add in an a value. I need to know what value here gives me the specific equation where if I plug in 1, I get out -9. However, I'm going to go ahead and ignore that a value for right now, and I'm going to start multiplying this out. Okay, multiplying complex conjugates, you square the first term, so that's just x squared, and then plus square your b, which in this case is 9. So I've multiplied those two together. That should be pretty quick. And then now I'm going to go ahead and distribute. So I have x squared, oh, sorry, not x squared. I have x to the third, right, plus 9x plus 2x squared plus 18. And then I still have this a value. And now I'm ready to go ahead and find the a value. Okay, so I know that if I plug in 1 for x, I should get out -9. So if I, let's do it this way. If I plug in 1, so I'm just going to plug in 1. So I have a times 1 cubed is just 1, plus 9 times 1 is 9, plus 1 squared is 1 times 2 is 2, plus 18. So if I know that I plug in 1, I have to get out -9. And I'm just going to solve. So I have 10 plus 2, 18. So I get 30. So 30a is equal to -9. Divide, I get -9 over 30. If I simplify that, I get -3 over 10. So I know that a, 10, that's a 10, there we go. I know that a is -3/10. So now I'm ready to go ahead and write my function, right? I know that a is -3/10, and because it's like a nasty fraction, I'm not going to distribute it in, okay, to this parenthesis. If it was like 4 or something, I would go ahead and multiply this in to make it 4x cubed plus 36x, right, plus 8x squared. But since it's a gross fraction, I'm just going to leave this as -3 over 10 times x cubed plus 2x squared plus 9x plus 18. And then I'm just going to call it a day. So again, if this number right here was like a 2 or a 4 or -7, something easy, I would then distribute it in. But since it's a fraction, we're not going to. Okay, moving on to the next one. So again, make sure you're pausing the video if you need to, right? Stopping and trying it yourself if you'd like, things like that. Okay, so we're going to look at the difference quotient again. Remember that this first term right here, this is what I'm going to focus on first. This tells me I'm just going to plug in x plus h into the f function. So every time I see an x, I'm going to replace it with x plus h. Okay, so I have, instead of x squared, it's x plus h squared plus 11 times, instead of x, it's going to be x plus h minus 7. So there is this circled term. Okay. So all I did was replace x plus h into the function. Then I'm going to subtract f of x. Well, f of x is just the original function, so I'm just going to subtract the original function, which is x squared plus 11x minus 7. And then this is all over h. I'm going to have to try to conserve space here, so let's see how we go. Okay, x plus h squared, hopefully we remember, we did it in our notes. It's x squared plus 2xh, oops, h, plus h squared. Okay, and then 11 times x is 11x. 11 times h is 11h minus 7. And then I can also distribute this negative, so that gives me negative x squared. Pin's starting to cut out. Minus 11x plus 7. So I distributed the negative there. And this is still all over h. So now here I can cancel some things. I have x squared and negative x squared. I have negative 7 and positive 7. And I have negative 11x and positive 11x. So all that gets to cancel, which leaves me with 2xh plus h squared plus 11h all over h. On the top here, I can factor out an h. I can't just cancel out h's, but I can factor out an h from the top, which leaves me 2x plus h plus 11 over h. Now I can cancel the h, okay, which leaves me 2x plus h plus 11. And there's nothing I can combine here. I can't combine like terms. There's nothing really I can do. So that's what I'm after. That's what I'm looking at. And that's my answer. Okay, and then last one, suppose you want to buy a used car that costs $28,800. The expected depreciation of the car is 20% per year. Determine the decay factor, write an equation, and estimate the depreciated value of the car after 6 years. First of all, 20% a year is a lot to depreciate, so just so we know. Okay, so the first thing it wants us to do is find the decay factor. So the decay factor is just 1, and then because it's decay, I'm subtracting. Okay, if it was growth, I would add. Okay, so it's 1 minus, and then your percentage, but your percentage as a decimal. So my decay factor here is 0.80. Okay, had 100%, subtract 20%, I'm left with 80%. And now this is just an exponential function. Hopefully we remember how to do all this, right? Where my starting value is 28,800. Then I multiply by my decay factor to the x. There's my equation. So I wanted that too. Then it wants to find the estimated value of the vehicle after 6 years. So now I'm going to take my 6. Oh, my pen is jumping. I'm so close to being done. Okay, I'm going to take my 6 and I'm going to plug it in for x. There's a lot of 8s going on, right? And then 6. So if I do 0.8 to the 6th, and then I multiply that by 28,800, I get about $7,549.75. And that is the value of my car after 6 years. You must, like, somebody's got to be beating up on their car real good in order for it to be depreciating by 20% a year. Okay, anyway, that's it for our mixed review. That's it for 3-1. I know that was a little bit longer than normal. At least it felt like it was longer for me. If you have any questions, make sure you reach out. Otherwise, good luck on the practice, and I will see you guys soon.